Good evening, everybody. I'm Steve Barrett. I'm a Senior Research Fellow at the University of Liverpool, working in the Department of Physics. So I'm not an astrophysicist. I'm a physicist with an interest, a lifelong interest, you might say, in astronomy. So a professional physicist, an amateur astronomer. And I give a number of these outreach talks, usually in person, but over the last year and a bit it's been a bit unusual, so I've been given lots of these Zoom talks. So this particular talk is obviously about the Hubble Space Telescope, and there are probably very few people who are not already familiar with that iconic image. Not necessarily simply astronomers, but I would argue that you could probably stop the man in the street and you would also be able to get them to recognise this particular scientific instrument. What I'm going to be talking about this evening is introducing the idea of a space telescope, why we need a space telescope, why we can't get by with simply ground-based alternatives. Be looking a little bit about the history of the Hubble Space Telescope, why the mirror was originally flawed and how they fixed the optics. Thinking about the legacy in terms of what has the Hubble Space Telescope done for our understanding of how the universe works. That, of course, is an enormous amount in 30 years of operation, so I'll just be picking out a few isolated topics. And then thinking about how the public is along for the ride. And I'll finish by going back to where I started, asking about future space telescopes and ground-based alternatives. Let's just have a think about how the sizes of telescopes square up with each other. This is a very useful indication of the relative sizes of the collecting area, which is basically mirrors with the exception of the very top left-hand corner, which is the 40-inch Yerkes lens in the Yerkes refractor. Everything else here is an indication of the relative sizes of the collecting mirrors of various telescopes. From the 100-inch Hooker in the top left, the 200-inch Mount Palomar, you can see that coming online fairly soon we have absolute monster telescopes coming along. The largest telescope at the moment is the one shown in yellow in the top middle, the Gran Telescopio Canarias on the Canary Islands. That has a mirror, strictly speaking it hasn't got a diameter, but it's an equivalent to a diameter of a little over 10 meters. And you can see that it won't be long before we have mirrors of diameter about 40 meters coming online in just a few years. So some telescopes are absolutely huge, but if we look at space telescopes, those are the ones down in the bottom left-hand corner there. The Hubble, you can see, is tiny by comparison with all of the telescopes that are indicated in this diagram. In the extreme bottom left we have the James Webb. I'll be just saying a few words about that right at the end of the talk. And there are two other space telescopes, Gaia and Kepler. Again, I'll just say a few words about those towards the end. So we know, of course, being amateur astronomers, we know that telescopes have come an awful long way in the 400 years since the telescope of Galileo. And refractors, which eventually gave way to reflectors, have got larger and larger over those 400 years.
Recording in progress.
Okay. Telescopes have been getting larger and larger from originally the lenses, the refractors, up to the reflectors, taking over once lenses got to about a meter or so in diameter, because it's impractical to have any lenses larger than that. So there has been a continuous drive between larger and larger optics, and the reason we want telescopes with large lenses or large mirrors is essentially twofold. One is that the larger aperture can collect more light, and so we can see fainter objects, but also larger apertures have higher intrinsic resolution, which means we can either see more detail, or we can see smaller objects, or we can see that detail in more distant objects. So there's a sort of double whammy. We collect more light, so we see fainter, and we can see more detail. So there's always the drive to larger and larger telescopes. But as we've seen, there are some huge telescopes on the ground, so why would we bother putting a relatively small telescope into Earth orbit? And I'm sure you know the answer to that. Even though the Hubble only has a mirror of about 2.4 meters in diameter, it is worth putting a telescope of that size into orbit simply because it is then above the Earth's atmosphere. The Earth's atmosphere doesn't absorb much of the visible light, but it does distort it. So we're still collecting the same amount of light, but we can see more detail if we put a telescope above the distorting effects of the Earth's atmosphere. And just to give you a rough idea of how dramatic that can be, for the Hubble Space Telescope, 2.4 meters in diameter, the resolution is of order 10 times better being above the atmosphere than a similar sized telescope if it was put on a mountaintop somewhere, still with a lot of atmosphere above it. The resolution would be some 10 times worse than the Hubble can achieve. So although we haven't got the light gathering power of large telescopes, we are getting the resolution, the detail. So where does the history of the Hubble Space Telescope start? Perhaps a little bit earlier than you might have appreciated. As far back as the Apollo moon landings, NASA was planning for a large space telescope, at the time simply called the LST. So whilst men were still bunny hopping on the moon, plans were afoot to build a large space telescope. It was realised, of course, many decades ago that if we can get away from the disturbing effects of the Earth's atmosphere, we'll have a much better telescope. So the first milestone was to start planning for it. Any guesses what the second major milestone was for the Hubble Space Telescope? Yep, it was cancelled. 1974, Congress withdrew all funding, saying, "Great idea, NASA, wonderful idea, fantastic science, putting a telescope in orbit. We can't afford it." So it was cancelled. There was then an outcry from scientists, which got almost ignored, but eventually politicians got on board, and it was realised that we really do need to go ahead with a project like this. And the funding problems led to a collaboration between NASA and ESA. So although quite often people think of the Hubble Space Telescope as being a NASA project, it is a NASA/ESA project. So in 1978, Congress reversed their decision and said, okay, we will go ahead with this, providing we get a certain chunk of money from ESA. And it went out to tender, and the spacecraft, it was agreed, would be constructed by Lockheed and the telescope by Perkin-Elmer. So of course everybody thinks of the Hubble Space Telescope as simply being a telescope which is up in orbit. But as far as NASA or ESA is concerned, strictly speaking, it's not a telescope with solar panels, it is a spacecraft. And it's a spacecraft that happens to have a telescope inside it. And when it comes to constructing an object like that, you do need to separate the expertise. So it was agreed that Lockheed had expertise in building spacecraft, so they were the spacecraft construction company, and the optical telescope assembly was given to the firm Perkin-Elmer. Construction of the primary mirror began in 1979, and it was appreciated very early on that we've got to get this right. Congress said if we're going to fund a space telescope, it is absolutely critical that the primary mirror is made and works perfectly. And so they said we have to have a backup plan, we have to have mitigation. So yes, we'll give the contract to Perkin-Elmer. In the late 70s, Perkin-Elmer started making the mirror, and in 1981, Perkin-Elmer declared that the polishing of the mirror was complete and the mirror was fantastic, the best mirror ever made. Up to that point, the backup plan was to make a second mirror. And when Perkin-Elmer said, our mirror is fine, the backup mirror, which was being made independently by Kodak, that was basically put on ice. That mirror was then mothballed. Up to that point, Kodak were making a mirror of the same size, making it to the same specification, hopefully to the same perfection that Perkin-Elmer had declared. But once it was realised that there was no longer a danger of the mirror not being made to specification, then the backup mirror was mothballed. A decision they may have regretted sometime later. 1983 came along, and that was the original planned launch date for the Large Space Telescope. At this point, it was renamed or named the Hubble Space Telescope, of course in honour of Edwin Hubble, who had done so much work looking at the expansion of the universe and the recession of distant galaxies. There were then a few delays. In 1984, the launch date was put back, mainly due to a few slips on the scheduling from Perkin-Elmer, and then there were a few delays due to Perkin-Elmer and Lockheed, so again the launch date was put back. By 1986, the budget had already exceeded $1 billion and was still going up. 1986, some of you will remember that date. That was the date of the Challenger disaster, which meant that the shuttle fleet was grounded, and therefore until the shuttles were launched again and then the backlog of all of those satellites that were due to go up was cleared, it took quite a few years before the Hubble Space Telescope finally got its slot to go into orbit. And indeed it wasn't until 1990 that it found its slot back into Earth orbit. By this point, it was estimated that the total construction costs were something of order $2.5 billion. And I believe that figure was just up to that point. It didn't include the costs of, for instance, service missions from the space shuttle. So a very expensive telescope. Before moving on, let me just make a little detour about the design. The Hubble Space Telescope is a so-called Ritchie-Chrétien design. This means that the primary mirror is not spherical, it's not parabolic. The primary mirror is a hyperbolic shape. And that means it differs very slightly from what you might consider to be the optimum way of focusing light from a distant source, which we all think about as a parabolic mirror. In fact, the last really big telescope to have a parabolic mirror was the Hale telescope on Palomar Mountain, which has got a 5-metre or a 200-inch mirror. At the time, when Hale was putting together the Hale telescope, or the 200-inch as it was called at the time, the 200-inch telescope was being designed with a parabolic mirror, even though it was known that if you take a hyperbolic mirror, specifically if you take 2 hyperbolic mirrors, you should be able to produce an optically superior telescope. But Hale wasn't prepared to take that chance at the time, back in the 1930s and 1940s, so he more conservatively decided to stick with a parabolic mirror. A parabolic mirror is known to have certain aberrations, which can be fixed by a hyperbolic arrangement of mirrors in the Ritchie-Chrétien design, but Hale decided to go with tried and trusted parabolic mirror. Ever since then, essentially all major telescopes have gone with a hyperbolic mirror design. Why am I telling you this? Well, because a parabolic mirror can focus light from infinity to a point, and it's relatively easy to test that it's doing its job correctly. But a single hyperbolic mirror can't be tested in the same way. And therefore, testing a hyperbolic mirror system is more problematic, and that's important for what comes next. Only when the telescope was in orbit in 1990 did the horror slowly dawn on those responsible for commissioning the telescope. They could not get it to focus. What they were hoping for was an image looking a little bit like what's on the left, hopefully a whole load of pinpoint stars. What they were actually seeing is something closer to what was on the right. Most of the light appeared to be focused into pinpoint stars, but every star had a halo around it. On the fainter objects, the halo wasn't so obvious, but behind every bright star, as well as the pinpoint of light, there was a horrible halo of light. Perhaps 90% of the light was focused correctly, but something of order 10% of the light was spread over a huge area. It eventually was admitted that the mirror was made with spherical aberration. Let's just make sure we understand what spherical aberration is. It's a particular fault which occurs for spherical mirrors, but that doesn't mean that the Hubble Space Telescope was made with a spherical mirror. Spherical aberration refers to what happens when light hits different parts of a mirror. So let's just imagine we have a perfect mirror here. It's supposed to be perfect in the sense that it will take light. Let's imagine it's parabolic, so it should be focusing light coming from the right-hand side to a particular focus in front of the mirror. And here we're seeing some of that light coming to a focus. But spherical aberration occurs when light hitting a different part of the mirror comes to a focus at a different point. In this particular case, light hitting approximately halfway from the centre to the edge is coming to a focus just a little bit in front of the focus that I showed you originally. And the further away from the centre of the mirror you get, the more exaggerated the effect becomes. So if we take light hitting close to the edge of the mirror, you can see that's coming to a focus a long way in front of the two light rays I've shown up to this point. So that is the essence of spherical aberration. Light hitting different parts of the mirror come to different focal points. If you, excuse me, if you like, it does not have a unique focal length. So where would you put your detector? You could say, well, let's put the detector where most of the light is. Well, a lot of the light is not focused at that point. We could say, well, let's move the detector to where most of the light appears to be focused. Perhaps 80 to 90% of the light appears to be focused where that detector is shown there. But you can see light hitting the edge of the mirror is coming to a premature focus and then diverging to produce this halo that we showed on the previous slide. That's effectively how it was diagnosed. That's a classic sign of spherical aberration. So remember, what they wanted to see was nice pinpoint stars with no signs of this halo. It was pointed out at the time, well, yes, we do have a problem. Most of the light is being focused correctly, but a little bit of it appears to be blurring the detail. Bear in mind that we are still doing better than we would see if we were on the Earth. The top panel of these three shows what you would expect from the same field of view if a telescope of this size was used within the Earth's atmosphere. In other words, if you took a 2.4 metre diameter telescope and put it on top of a mountain, that's the sort of resolution you would get. So the Hubble was doing better than a telescope on Earth. Well, yeah, duh. But they've just spent $2.5 billion putting this thing into orbit, only to find it's doing a little bit better than it would have been if you had left it on Earth in the first place. Taxpayers in America and in Europe would not be happy with that sort of argument. How can such a mistake be made? How can you spend that much money and make a mirror that doesn't focus correctly? Tests carried out during construction by Perkin-Elmer indicated it was the most precisely figured mirror ever made, with a surface roughness, in other words mountains and valleys, in this 2.4 metre diameter mirror, which were only about 10 nanometers or so in size. That was absolutely state-of-the-art in the 1980s. It's still pretty good going, even by modern standards. And if you're finding it difficult to work out what 10 nanometers, 10 billionths of a metre, for roughness means on a mirror the size of 2.4 metres diameter, think about taking that mirror and scaling it up until the mirror is the size of the Earth. How big would those bumps be then? Well, the bumps would be about 2, 3, 4 centimetres in size. That's the roughness of something the size of the Earth. So you can see that absolutely it is a very, very smoothly figured mirror. But it's very precisely the wrong shape. They wanted to make a hyperbola of a particular shape. They got it wrong to the extent of approximately 2 microns. 0.002 of a millimetre. And if that doesn't sound like much, remember that the wavelength of light is about half a micron, and therefore 2 micron error in the shape of the mirror means that it's wrong by about 4 wavelengths of light. Not a tiny fraction of the wavelength of light. You would really like a mirror to be accurate to a 20th or a 30th or a 40th or a 50th of the wavelength of light, but instead it's wrong by 4 wavelengths. There is no way a mirror like that could ever focus correctly. So how can Perkin-Elmer make a mirror so precisely wrong? Well, we come back to the fact that the mirror isn't simply a parabola. You can't take a distant object and focus with a parabola to make a star when the mirror is not a parabola. If the mirror is a hyperbola and it's a hyperbolic shape, you need to do a test using some additional optics. We're not going to worry about the details, but the additional optics needed in the test rig is called a null corrector. It's a way of fooling the test rig into thinking it's dealing with a mirror that should focus, even though a hyperbolic mirror doesn't focus without a second mirror, the secondary of the telescope. There's no way you can really test two mirrors at the same time. You have to test them individually. So you use a null corrector, a set of optics in the test rig. What was the problem? The null corrector was misplaced. In the test rig that Perkin-Elmer set up, the null corrector was misplaced by about 1 millimeter. The thickness of a washer misplaced the actual position of the null corrector. A laser interferometer was supposed to be checking that it was in the correct place, but the laser interferometer was picking up a reflection because a little bit of paint had flaked off, and it didn't correctly pick up the fact that the null corrector was in the wrong place. So the test rig was set up wrong, so the test rig was giving the wrong results. Oh. A much simpler test would have revealed the fault. The null corrector in the test rig was a very expensive test rig. A much simpler test would have told them that something was wrong with the mirror. But Perkin-Elmer said, we've just done a very expensive test and that says everything is hunky-dory. Why would we do a much cheaper test to cross-check it? Everything is fine. So there is a backup mirror made by Kodak. It's been tested, and because it was done completely independently without the same test rig, one assumes that they wouldn't have made the same mistake, and the Kodak mirror was presumably made correctly. But the Kodak mirror is sitting in a museum somewhere, and the Perkin-Elmer mirror with spherical aberration is sitting in the Hubble Space Telescope in orbit. What a disaster. It could have been the end of not just the project. It is speculated that it could have been the end of NASA. If they hadn't figured out how to correct this, it's possible that Congress would simply have said to NASA, not only no more money, they would have basically just shut it down completely and said, that's it. We're not just pulling the plug on the Hubble project, we're pulling the plug on NASA. If you can't get this right, you don't deserve the money. So there was a lot of pressure on designing a fix and a lot of pressure on the astronauts to go up in the shuttle and fix the telescope. The one thing that absolutely saved them from complete disaster was the fact that from the outset the Hubble was designed to be serviceable by shuttle astronauts. As well as having cameras and spectrometers on board, sitting on the ground was not the flight version, but a backup version, if you like, of the camera, the wide field camera. And this is it here. So what they had was the option to say, well, we know there's a problem with the telescope in orbit, but we know precisely what the problem is. We've gone to Perkin-Elmer, we've looked at the test rig, and we figured out the test rig has got this problem. And therefore, we know the mirror has been made wrong, but we know precisely how wrong it is. And therefore, if we wanted to, we can supply it with corrective optics. Because we know precisely what the problem is, we know how to fix it. And one option is to say, we've got a camera which is essentially a duplicate of the one that's in orbit. If we've got one on the ground and we know what the problem with the mirror is, we can change the optics of this camera. In other words, the light comes and hits this mirror and then goes into the camera. If we can add some optics to this camera, we should be able to get this camera to work even with the faulty mirror that's up there. So they designed a solution that will make this camera work with the faulty mirror. That, they figured, would be a solution for the camera. But the Hubble Space Telescope is not simply a telescope with a camera, it's got multiple cameras and multiple spectrometers. So fixing one that's on the ground is fine, but what do you do about all the other instruments that need fixing as well? Well, they came up with a solution, which they called a set of corrective optics, or COSTAR, and they figured that we can add these corrective optics as long as we sacrifice one of the instruments that's currently in use. We have to throw that away to make space for a corrective set of optics. This is the actual optics themselves, because they are in a museum. They were sent up and then brought down again. I'll say that again a little later. If you can't see what that is, there's a little model in the museum that makes it a little bit clearer what's going on. It's a sort of Swiss Army knife of corrective mirrors. So if light was coming from the telescope to an instrument, there were a number of arms with mirrors on the end which would swing into position to provide an extra reflection, with a mirror not flat but slightly curved in just the right way to correct for the optical error of the main mirror. And you can see there are a number of arms coloured here, and that's because there are a number of different instruments at the back end of the Hubble Space Telescope, and if you wanted to send the light from the mirror to this instrument, you would bring this arm down, which would put a mirror in this position to send the corrected light to that instrument, and if you wanted to swap to a different instrument, that arm would retract and a different arm would come out with a different mirror to send the light to the other instrument. So as long as you're prepared to sacrifice one of the instrument payload bays, you should be able to put this corrective optics in, and then you should be able to send corrected light to all of the remaining instruments in the Hubble Space Telescope. So as I mentioned just a moment ago, you mustn't think of the Hubble as simply being a big camera. At any given time, the Hubble Space Telescope will have at least 2 cameras and 2 spectrometers, or spectrographs, on board. Now, the actual cameras and spectrographs have been swapped in and out, as I'll show you shortly, but it is always a multiple set of instruments that need to be dealt with. So I'll show this a little bigger in just a second, but one thing to bear in mind is that the instruments, for instance, the camera itself, the most recent camera that was installed in the Hubble Space Telescope, has a CCD chip approximately this size. It's about 4 centimeters square. Quite large for an astronomical instrument, but by no means large compared to, for instance, the chip that might be in your digital SLR camera. But bear in mind that although this is a relatively large chip, when you think of it with the focal length of the Hubble Space Telescope, the focal length is nominally 58 meters. So if you think about this at the end of a 58-meter focal length, it makes you appreciate just what a small field of view the Hubble Space Telescope has. Let's just blow that up a little bit so we can see it in a little more detail. Remember what I said a while ago, this is not strictly speaking a telescope, it's a spacecraft with a telescope inside it. And here you can see that the telescope actually only occupies, what, half of the total length here? The secondary mirror is a long way back from the front of the telescope, gives you a fairly good lens hood, as it were. And the primary mirror is not at the back end of what you tend to think of as the back end of the telescope. The primary mirror is actually here, about 2/3 of the way down. Everything else is instrumentation. There are various cameras and spectrometers, and there are other pieces of equipment to make sure that the telescope is pointing in the right direction when it's commanded to point at a particular object, to take a spectrum, to take an image. It has to be, of course, held very precisely in that position. Let me give you an idea of just how complex the service missions were, in the sense that the first thing the astronauts had to do was to fix the problems we've just described. It was launched in 1990, and these bars here show you various aspects of the instrumentation. I'm not going to go through the detail of what they are. They are either cameras or spectrometers, or as you can see from the 3rd and 4th entries there, I've just labelled them gyros and electrical systems to remind us that those need servicing as well. And you can see here that we've got a timeline from the launch 30 years ago in 1990 up to essentially the present day. This particular one goes to 2020. I'll come to that in just a second. So the first thing that happened is the first service mission replaced camera 1 with camera 2. Camera 1 is of no use because it won't focus correctly. Camera 2 was the one that was on the ground, where they realised that if we put corrective optics in camera 2 and put that in the telescope, it should work fine. And lo and behold, they put camera 2 in and it worked a treat. The problems with the optics were fixed. This particular instrument bay here, this had to be thrown away. It was actually a photometer. It doesn't matter too much. They decided that was the one that would have to be the sacrificial lamb. They threw that away and replaced it with CoStar. CoStar, the Swiss Army knife of corrective optics that would allow corrected light to go to whichever instrument they wanted. On this particular green line, I've shown with an asterisk simply the fact that whilst the astronauts were there, they did a little bit of tweaking. They fixed some problematic gyros, they fixed some of the electrical subsystems that were having problems at that particular time. A few years later, the second service mission, you can see down here, let's not worry about what these instruments are, except to say that if it ends in an S, the acronym probably indicates that we're dealing with a spectrometer, and if it ends in a C, the acronym probably indicates we're dealing with a camera. So what happened in the service mission 2 of around 1997, one spectrometer was changed out with another, and this spectrometer was swapped out for another. So why would you go up in 1997? The Hubble Space Telescope has only been up for a few years. Why would you replace one spectrometer with another? Well, remember, it's only been in space for a few years, but remember, it was designed in the 70s, built in the 80s, and launched in the 90s. Which means by 1997, some bits of it are already getting old. And technology always moves on. So they were able to put in improved spectrometers, so they took advantage of Service Mission 2 to replace 2 spectrometers with 2 state-of-the-art spectrometers. Service Mission 3A was supposed to be just a little bit of a tweak, and you can see that there's an asterisk there because again they were having problems with the gyros. They fixed some of the gyros but essentially did very little else. The grey that I've shown there against one of the spectrometers indicated that shortly after that service mission they started having problems with that spectrometer. So, okay, they've got 2, so it's not the end of the world, but taking spectra is very important as well as taking images. Images show you what something looks like, a spectrometer tells you what it's doing or what it's made of, so a very important aspect of the whole Hubble mission. So they were having problems with that particular spectrometer. Service Mission 3B, they tweaked some of the electrical systems and fixed the spectrometer that was causing problems. And the final piece of instrumentation that was swapped out on that 4th service mission was the FOC, one of the cameras. It looks like they've replaced it with a spectrometer, but they are simply playing around with these acronyms. ACS, although it looks like a spectrometer, is actually a camera, Advanced Camera for Surveys. So they've replaced one camera with another. So at this point, after 4 service missions, some, 13 years after launch, they have now replaced every piece of instrumentation with a new piece of instrumentation which has got on board all the optics need to correct for the errors in the main mirror. So at this point, there's no longer any need for CoStar because every instrument has been swapped out with a modern replacement which has all the corrective optics that are necessary. There were some arguments as to whether or not there should be another mission, but things started to fail in the next few years. You can see that one of the spectrometers failed, one of the cameras failed, they had problems with electronics. So in 2009, after a little bit of argument as to whether or not there should be a 5th service mission, it was finally agreed there would be a 5th and final service mission to the Hubble Space Telescope. So Service Mission 4 in 2009 replaced Camera 2 with Camera 3. That's the one that has the largest chip that I showed you just a moment ago. That's the camera number 3. They no longer need CoStar. Remember, the Swiss Army knife is now redundant because every instrument has its own corrective optics. So CoStar can now be taken out, brought back home again and put in a museum. That's the photograph I showed you earlier. And if you're going to free up one of the instrumentation bays, we may as well fill it with something. In goes another spectrometer. You can see how important spectroscopy is, because we now end up with 2 cameras but 3 spectrometers. Whilst they were there in 2009, they tweaked the gyros, they fixed some electronic problems, they made sure the spectrometers and the cameras were all working as close to perfectly as possible. One critical thing they did in 2009 is also replace some of the electronics, explicitly some of the power supplies and backup computers that were there just in case they had problems. And perhaps you have read recently that although they've been working for the best part of a decade without any serious problems, in the last month or so they had a critical problem, which basically means that the telescope couldn't work anymore because of problems with the main instrumentation computer, the so-called payload computer. Turns out it probably wasn't the computer that was actually faulty, it was probably the power control systems that were feeding voltages to the computer, but they have now switched to the backups that were actually installed in 2009 and haven't been used for, what, 12 years or 13 years? And so they switched to those, and now everything appears to be, fingers crossed, working nicely. So although they've been running very nicely, those problems were critical in the sense that it might have shut down the telescope. We're now hoping that now that they've switched to the backup power supplies and backup electronics, they might be able to get the instrumentation working again and hopefully get back to normal operations, and let's hope continue for a few more years yet. So that's the history, effectively. How has the Hubble Space Telescope contributed to extending our understanding of how the universe works? There are far too many examples, so I'm just going to pick a few of them and say a few words about each of these. Excuse me just one second. Okay. This might look like a little section of the Milky Way. Actually, it's a little bit of the Andromeda Galaxy. And the Hubble Space Telescope has got the ability to see a number of individual stars in the Andromeda Galaxy, and it's picked out those stars that have a particular variation. They're so-called Cepheid variables, whereby the variation of the luminosity, the period of the variation, is a function of how bright the star is. If you can find a number of these stars in a remote galaxy like Andromeda, if you monitor their brightness as a function of time and look at the periodicity, by comparing with similar stars in our own Milky Way galaxy, we can work out how bright those stars must be. And if we know how bright they are, and we know how bright they appear to be, we can get a distance, because a bright star that's at a great distance will of course look fainter. And so the Hubble Space Telescope was able to get the distance to the Andromeda Galaxy far more accurately by monitoring lots of these Cepheid variables compared to any other telescope previously. And if you can work out the distance to the Andromeda Galaxy accurately, it gives you the first rung on the ladder of working out all the distances to all the galaxies in the universe. So for the first time, the Hubble Space Telescope was able to get an accurate measure of how big the universe is. And because we can measure the recession velocity, the rate at which galaxies are moving away from us, as first determined by Edwin Hubble back in the 1930s. If we can measure that from spectroscopy, and now the Hubble Space Telescope is able to give us distances, then we can get the Hubble constant, the value of the recession velocity divided by the distance. It tells us how fast the universe is expanding. That could now be determined accurately. Before the Hubble went into orbit, we didn't actually know how fast the universe was expanding, particularly accurately, and we didn't know how old the universe was. In other words, it was somewhere between 10 and 20 billion years old. But once Hubble had made these measurements, we got an accurate indication of the size of the universe, and now we know that the universe was born some 13.77 billion years ago, much more accurately than was known previously. We tend to perhaps take exoplanets for granted. We know that there are thousands of exoplanets out there. But remember, exoplanets were unknown. They were purely theoretical before Hubble went into orbit. The first exoplanet wasn't found until about 1995. So this was a very early image taken in the early noughties from Hubble, in which it's actually directly image exoplanets. Most exoplanets that have been found by spectroscopic means, or by looking at the brightness of stars dimming as a planet goes in front of a star. But Hubble, because of its fantastic resolution, is one of the few telescopes that's able to actually image exoplanets, and this was done for the first time back in the early noughties, where it looked at a star. It looks very odd to have all of this scattered light that we can see here. The actual very bright central star has been masked out and a little dot has been put where the star is. But if you look in that little section on the right, they've imaged a point, and 2 years later that point has been moved, and they've determined that this is a planet a long way from its parent star, moving in a very large elliptical orbit. And you would need to have fantastic resolution in order to resolve a planet at that distance from a star. Not only can Hubble actually see exoplanets, it's able to do what very few other telescopes can do, and that is it can take a spectrum of an exoplanet by looking at light coming through the atmosphere of a planet, and it's done this for a number of different systems in order to try and work out what is the chemical composition of the atmospheres of these planets. So again, finding a planet exists is one thing, but if you can take its spectrum, then you can start to think about what is that planet actually made of. Does it have oxygen in the atmosphere? Does it have methane in the atmosphere? Does it have water in the atmosphere? Something that you can do with spectroscopy that you can't do purely with imaging. And of course, Hubble has taken I don't know how many images of distant galaxies, galaxy clusters and individual galaxies to try and get a better handle on how galaxies have formed. Galaxies that are close to us where we can see exquisite detail, and galaxies that are somewhat further away, and we're looking further back in time, of course, the more distance that the light has to cover, so we're looking back in time. We can get an idea of galaxy formation and galaxy evolution, and try and understand why some galaxies appear to be quite different structures from others. Here's a wonderful picture that got a little bit of publicity, but perhaps not as much as it ought to. This is an image in which Hubble appears to have imaged a galaxy here in which there are 4 supernovae going off. Now, what's the chances of one galaxy having 4 supernovae, given that most of the time you would expect in any given galaxy a supernova to go off maybe once every century or so? What's the chances that 4 go off at the same time? Very unlikely. And it was realised that what we're actually looking at in that image is a lensed image of a more distant galaxy. In other words, a supernova has gone off in a galaxy, and light from that galaxy has taken different routes to get to us, or to the Hubble Space Telescope, and those different routes are a consequence of the fact that light has passed through this galaxy cluster, which is bending the path of the light. Or if you prefer, the galaxy cluster is bending space and then the light is following the curve of space. Different way of looking at it. And so what's going on with these 4 points of light here at the bottom pane is that we're looking at the same supernova that's been lensed because light has taken a slightly different route to get to us. Not only that, but if we think about the fact that the light that's taken this route, for instance, if you can see my cursor at the top here, the light from the distant galaxy which has taken the longest dogleg route, that would have taken longer to reach us. So if we see a galaxy here and it appears that a supernova has gone off, then this up here in the top left is the same galaxy. It's imaged separately because the light has taken a different path to reach us because of the bending of light, the so-called gravitational lensing. And if light has taken a longer path, it will take longer to reach us. And there's no sign of the supernova in that particular image because the supernova hasn't gone off yet in that particular image. It's gone off in the shorter route, but because theorists are able to say, well, I think it's going to take 6 months longer for the light to reach us via that other route, the dogleg, then we can predict that if the supernova has gone off as viewed in the right there, we can predict that in 5 or 6 or 7 months' time, we are going to see a supernova go off in that galaxy in the top left. This was, I think, the first time it's ever been possible to say we know that a supernova is going to go off shortly. Let's watch that galaxy, and then we can see a supernova go off right from the outset. Not catch it a few days after it started when it's got bright. We can catch it right from the beginning. So they didn't know precisely what the date was, but they instructed Hubble to go back to look at that galaxy a few months later, and I think it was something like 5 months after that. Yep, they saw the supernova go off in that galaxy. So it's not only amazing that you can see these gravitational lensing effects, it's amazing that you can use them to predict what you're going to see because of light taking different paths between a very distant galaxy and us. The Hubble Deep Field, perhaps I won't talk too long about that because it's a well-known picture in which Hubble stared at a region of space for something like 1 million seconds, thinking that there might not be much there, but as well as picking out a couple of stars, we've picked out thousands upon thousands of galaxies. Some which are quite close, some which are very remote. So this is very much a look back to the very earliest parts of the universe. We're looking back perhaps up to 13 billion years. The universe, 13.8 billion years old. We're going back, way back to the first billion years of the universe's existence. This is a reminder of just how small the field of view is. If you take a chip no bigger than this and put it on the end of a 58-metre focal length, you get a field of view which is about the size of that rectangle there. You see a tiny fraction of the ½ degree that we can see in the full moon, or the 1 degree that we would see in a survey plate, for instance, taken from the surface of the Earth. And just to make sure it wasn't a fluke, as well as taking the Hubble Deep Field, they took another deep field in a different part of the sky and exposed and got a similar looking picture, which just reinforces the fact that when you look at large enough distances, the universe looks the same in all directions. It's effectively isotropic. It doesn't look any different if we look to the left or if we look to the right. There's nothing special about where we are. We can look in any direction and we see essentially the same thing. And this is another reminder that if you look at a large cluster of galaxies, if you have the resolution, not only will you make out all of the components of this cluster of galaxies, you see the telltale effects, these little blue streaks here, these arcs that look like they might be defects on the image. These are all images of more distant galaxies that have been lensed by the light bending as the light passes through this rather massive galaxy cluster. And the more of these type of images you look at, the more information you get about not only the visible the visible mass that must be there. The light tells us how much mass is there. We can work out how many stars there are in this cluster. But we find that the amount of mass we need to bend that light is far more than we can account for simply by looking at where all the stars are. And this is one of the strands of evidence that dark matter must exist. There must be more matter than is simply the luminous matter. And the universe appears to have far more of this dark matter than it does simply of the stars and dust and gas and galaxies that we can see. And Hubble has been instrumental in giving us the evidence for dark matter. As well as the scientific legacy of the Hubble Space Telescope, it's also brought the public along for the ride as well. The laws of physics have created these incredible structures, whether they be galaxies or whether they be nebula. The Hubble has revealed them. Through all the research, Hubble has brought the public along for the ride. It's taken the excitement that scientists feel with every new discovery and brought it home to non-scientists. That was on the 25th anniversary of the Hubble, a reminder that it's been an exceptionally productive scientific instrument, but also it has managed to keep the public engaged with what it is doing. Let's take a few minutes to remind ourselves of some of the wonderful images that the Hubble has produced in the last few years. In other words, some of my favourite Hubble images. The Helix Nebula, a planetary nebula in which a star has thrown off its outer atmosphere. Truly stunning image. the antenna galaxy here, the collision of two galaxies. We can see, because of the resolution of the Hubble, we can see all of the detail, especially all of these pink regions here, which are star-forming regions, reminding us that when two galaxies collide, it's not the end of days, it's actually the start of a whole new era of star formation that can give rise to a large number of new stars being born. The Crab Nebula, we knew about this supernova remnant, but the Hubble was able to image it in fantastic detail. Mystic Mountain. Similar to the Pillars of Creation, the Mystic Mountain is a region in which stars embedded in this gaseous region are sculpting these clouds and producing some jets and shock waves. It's a little difficult to see what those stars are doing because the stars are embedded inside these huge gas columns. And again, I'll say more about that shortly. The Sombrero Galaxy, simply one of my favourite galaxies, showing again in great detail the dust ring around the equator, if you will, the rim of this particular galaxy. A globular cluster, reminding us that in many cases, for most telescopes, when you look at a globular cluster, there are so many stars, especially in the core of the globular cluster, then you can't always see detail because all the stars overlap with each other. It's simply too crowded. And analysis of globular clusters is sometimes limited to those stars near the outside region where you can make out individual stars. But the resolution of the Hubble Space Telescope is sufficient that it can see individual stars even going into the heart, into the core of the globular cluster itself. A barred spiral galaxy, it happens to be NGC 1300, but it's simply reminding us that the Hubble has managed to image thousands upon thousands of galaxies in order to see structural detail and give us better understanding of how galaxies are born, how they form, how they evolve, and ultimately how they collide with each other. This is an example of a galaxy collision in which both galaxies have been significantly distorted by their proximity to each other, but they still give beautiful images. The Veil Nebula, an example of a supernova remnant. In this case, this is a composite image of lots of different colours, each taken at a particular wavelength corresponding to a particular element. I can't remember what's in this one. I would imagine this has been imaged at the hydrogen line, and oxygen and sulfur and other elements have been imaged and then combined together, with each element assigned its own colour to show you what a rich structure is in these supernova remnants. And of course the famous Pillars of Creation. An image was taken in 1995 and then the pillars were re-imaged for its 25th birthday with its new camera number 3, higher resolution, to show just what a fantastic structure this is. And again, I've mentioned this before, the Hubble Ultra Deep Field, being able to see back in time billions of years gives us a much better idea of how the universe is put together, how it came to be, and how it's evolved in the billions of years since the Big Bang. So where do we go from there? What lies beyond Hubble? Ground-based telescopes, especially these telescopes that have very large mirrors that I showed you earlier in the talk, in principle they could have, and these days they do have, adaptive optics that can compensate for the Earth's turbulent atmosphere. In other words, if you shine a laser, as indicated in this telescope image on the left, if you shine a laser into the sky, you effectively generate an artificial star. And if you watch how that moves because of the turbulence of the Earth's atmosphere, if you're lucky, you should be able to correct the optics to take into account the turbulent nature of the Earth's atmosphere. So if you can improve the resolution by using adaptive optics on ground-based telescopes, do you need space-based telescopes anymore? If you're coming along with a 40-metre telescope, you wouldn't necessarily try and move all of that 40 metres. You would apply the adaptive optics to perhaps the secondary or a tertiary mirror in the system. But if you can collect light over these huge areas, why would you bother with a space telescope at all? Well, it is true that ground-based telescopes can correct for the Earth's turbulent atmosphere, but the Earth's atmosphere is chaotic. If you shine a laser into the sky and generate an artificial star, you can work out how the Earth's atmosphere is changing at that particular point. But it'll be different over here, and it'll be different over there. So you can effectively only correct for a limited field of view around the artificial star. That's fine if you only need a limited field of view, for instance if you're trying to image an exoplanet. But if you want to get high resolution over the entire field of view that your telescope can see, then there's no alternative but to get rid of the Earth's atmosphere completely by taking the Space Telescope into orbit. And that's been done, of course, for a number of space telescopes. Let me just briefly say a few words about them. Kepler, of course, had a very specific mission to find Earth-like planets orbiting other stars. It did that not with a small chip a few centimetres on a side, but with a detector shown there, half the size of a coffee table, a large imaging system that stared at one patch of sky. It didn't attempt to survey the entire sky, it just stared at that part of the sky between Cygnus and Lyra. You can see Vega on the right there, and it simply monitored the brightness of these stars over a period of time and looked for the characteristic dips which tell you that an exoplanet has moved in front of the star and caused the light of the star to be dimmed. Gaia has also been up in space for quite a while now, and you may have heard that it has been returning data for the past few years. It has a very ambitious set of aims, and that is to stare at as many stars as possible. It's trying to work out the positions of as many stars as it can see, perhaps 1 billion or so stars. Okay, that's not all the stars in the galaxy, but that's still a pretty big fraction of them, and it's going to measure their positions to an accuracy of not arc seconds, not milliarc seconds, but to accuracies of less than a milliarc second, of order perhaps 25 microarc second accuracy. And where possible, it'll do some spectroscopic measurements as well, and because it will be repeatedly measuring the positions of those stars over the next few years, it will not only know the positions of the stars very accurately, it'll know how they're moving. In other words, it'll give us a three-dimensional map of the Milky Way, because we'll be able to see how stars are moving relative to each other. We hope to be able to produce a very accurate 3D map of the Milky Way before too long. So let's just reflect on the Hubble Space Telescope, if you'll excuse the pun there with the astronaut reflecting the Hubble Space Telescope. Where do we go from here? Is there a replacement for the Hubble? Well, I'm sure you're all aware that the James Webb Space Telescope has been on the drawing board for decades. It's been hopefully close to launch for quite some time now. It's been tantalizingly close to launch for quite a few years. The last estimate was hopefully by the end of October. It looks like that's going to have to be put back again, so we're not sure exactly when it's going to be going up. The James Webb Telescope is a significantly larger mirror compared to the Hubble. The Hubble, remember, 2.4 meters. The James Webb, something of order 6 meters, depending on exactly how you define the diameter. Significantly larger, but because this has got to go up inside the fairing of a rocket, it means that the mirror is going to have to be folded. It's already in segments, but some of those segments are going to have to unfold once it gets to where it needs to be. And unlike the Hubble Space Telescope, it's not going to be orbiting the Earth. It's going to be at one of these so-called Lagrange points. L2, Lagrange 2, is a location, you can see its position here, on the other side of the Earth from the Sun. So if we draw a line from the Sun to the Earth and keep going by about 1 million miles or so, we get to a point which is called L2. That's a point at which you can park a spacecraft. In other words, if you were to put a spacecraft there and basically get it to stay put, then it will move around the Sun in 1 year. In other words, it will be in sync with the Earth, and it will appear to be stationary relative to the Earth. Stationary in the sense of always on the opposite side from the Sun. That's where Gaia is doing its business at the moment. Gaia, strictly, it isn't parked at L2, it's doing a little orbit around L2, and the intention is to send the James Webb Space Telescope to the same place. They're obviously going to make sure they don't collide with each other. They're going to be far enough apart that that's not an issue, but L2 is a very convenient place to park things which need to be away from the Earth. Why do we want the James Webb Space Telescope to be there rather than Earth orbit? Because the James Webb Space Telescope is going to work mainly in the infrared, and the Earth is a hot object. The Sun, of course, is even hotter, but the Earth, you don't really want to be next door to an object which is at 300 Kelvin or so. You want to be as far away from as possible. And remember, the pictures of the James Webb show you that underneath there's a huge shield, a so-called sun shield, which is going to make sure that the heat from the Sun and the Earth don't interfere with the infrared experiments that are being carried out, the infrared images that are going to be taken by the James Webb, or indeed the spectra that are going to be taken. So what will the James Webb do? Well, why do we want to work in the infrared? It's not simply a replacement for the Hubble Space Telescope. There are a couple of reasons why we might want to work in the infrared. If we come back to the image I showed earlier of the pillars of creation, I mentioned that there were stars inside these pillars which are sculpting. The radiation from these stars are sculpting the pillars. But it's difficult to see what's going on inside anywhere that's got a lot of gas and dust. But infrared is better at penetrating these regions, and if we look at what we would see if we were to look at the pillars of creation in the infrared, the Hubble can work a little bit into the infrared. The James Webb will be able to just move much further than that. So this is an indication of what the James Webb will be able to do, as indicated by what the Hubble has been able to do up to this point. And you can see that now we can see inside these pillars and get a better idea of what's going on. Not only that, we'll be able to look inside the rather dusty environment, for instance, of what's going on when exoplanets start to form around distant stars. In visible light, it's very difficult to see what's going on. In infrared light, we should be able to look inside a solar system during its formation and get an idea of how the solar systems start to form. Not only that, but the James Webb will be able to do the equivalent of the Hubble deep field. And remember, I said we're looking back in time when we look at a set of objects like this, because the more distant objects, light has taken much longer to reach us. So some of these objects might be quite close, some of these objects might be a long way away. The more distant objects are receding from us, they are moving away from us because of the expansion of space. Many of those objects are moving much faster than the speed of light. Their spectrum is redshifted because of the so-called Doppler shift, or if you like, the cosmological redshift. The spectra from those stars is shifted to the red end of the spectrum. And if they're moving away from us at 2 or 3 or more times the speed of light, the shift can be rather extreme. And so if most of the light from a galaxy is around about the ultraviolet or the visible or the infrared, if you shift that, if you give it a large redshift because it's moving away from us so fast, that light can be shifted out of the visible and most of it will end up going into the infrared. So some of these very faint red objects that you might be able to see are just visible in visible light, but it's hoped that they'll be a lot brighter if we look at them in infrared light, because we'll be looking at the light that's been redshifted from the visible into the infrared. So it's hoped that the James Webb will be able to see some of these galaxies looking brighter simply because there will be more infrared radiation, but also perhaps the James Webb will be able to look back further in time because it will be able to see fainter galaxies which the Hubble Space Telescope is not able to see. Mainly because of the infrared and partly because of the fact that the mirror of the James Webb is so much larger than the mirror of the Hubble Space Telescope. So there are a number of things to look forward to when eventually the James Webb Space Telescope gets launched. So I gave you an introduction as to why we need space telescopes. I told you why the mirror was flawed. I told you how the optics were fixed using COSTAR and replacing the optics of all of the instruments which were swapped out. I gave you a very brief idea of some of the science that Hubble has told us about and how the public has been pulled along for the ride. And I've now finished with reminding you that yes, ground-based alternatives will be fantastic, but there will always be a need for space telescopes. Thank you all for listening.